Welcome back. I hope you had a great weekend. Let's get started with a new chapter. In chapter 15, we will talk about the chi-square statistic that can be used for tests for goodness of fit, but also for tests of independence. So the chi-square goodness of fit measures significance, so it tests for differences between two groups, and it's very similar to a one-sample test, but this one is for categorical variable. So in this case, we determine if our sample is similar to and representative of a specific population. The chi-square for independence measures relationship. It tests for a relationship between two nominal or ordinal variables. So this one is similar to the Pearson's correlation. And you can see I'm saying chi-square and chi-square. You will hear those different pronunciation of that word. After this chapter, you will be able to explain when to use a chi-square test. So when it is appropriate, you will be able to test hypotheses about the shape of a distribution using a chi-square goodness of fit. You'll be able to test hypotheses about relationships of variables using the chi-square test of independence. And you will be able to evaluate the effect size using phi coefficient or Cramer's V. In statistics, we have to make an important distinction between parametric and non-parametric statistical procedures. And the distinction is really important because if you get it wrong, you risk using an incorrect statistical procedure, or you may use a less powerful procedure. Non-parametric statistical procedures are less powerful because they use less information in their calculations. So for example, we have seen, and that's what we did so far throughout the semester, that a parametric correlation uses information about the mean and the deviation from the mean, while the non-parametric correlation will use only the ordinal position of pairs of scores. All the hypothesis tests we used so far tested hypotheses about a population parameter. And all the parametric tests share several assumptions. So we always assumed that there was a normal distribution in the population. We always assumed homogeneity of variance in the population, and that there was a numerical score for each individual. So we always had interval ratio variables. However, what do we do if a research situation does not meet all these assumptions? That is when we do a non-parametric test. And chi-square and other non-parametric tests do not state the hypotheses in terms of a specific population parameter. They make very few assumptions about the population distribution, so it's called the distribution-free test, and the participants are usually classified into categories, so nominal or ordinal scales are used. Non-parametric test data may also be frequencies. So sometimes it's not easy or possible to obtain interval or ratio scale measurements, or the scores violate parametric test assumption, or there's a high variance in the original score, or we have undetermined or infinite scores that cannot be measured, but they could maybe be categorized. Then we can use non-parametric tests like chi-square. The chi-square goodness of fit test uses sample data to test hypotheses about the shape or the proportions of a population distribution. It tests the fit of the proportion in the obtained sample with some hypothesized proportion of the population. With the chi-square, we specify the proportion or percentage of the population in each category. Our null hypothesis is always going to be that there are equal percentages or proportions among the various categories, and that there is no difference in the specified population from the proportions in another population. So here, for example, you can see the null hypothesis would be whatever the issue is, men and women think exactly the same way, right? 50% of men, 50% of women. That's a null hypothesis. There is no difference between the two groups. We will have a few new notation for the chi-square. So chi-square, the lowercase Greek letter of chi. And we will have FO for the observed frequency and FE for expected frequency. But how does this chi-square work? First, we have to construct a table of the expected frequency that are in perfect agreement with the null hypothesis. So what would it look like if the null hypothesis was true, meaning there is no difference between the categories? The FE is the value that is predicted from the null hypothesis and sample size. And we compare this with the FO, which is the frequency observed, which is our data set. And if the discrepancy between the observed and expected value is large, we can reject our null hypothesis. And we fail to reject the null hypothesis when the discrepancy between the frequency observed and the frequency expected value is small. This is the logic behind chi-square statistic. Just like before, we determine our alpha, so the significant level, again 0.05, 0.01, or 0.001, and then we locate the critical chi-square value. And you can find this on table 582. Chi-square is a family of distributions, and the distributions are determined by the degree of freedom. There's a slightly different shape for each value of the degree of freedom, as you can see here. You've got to remember that the degree of freedom for goodness of fit test is just C minus 1, where C represents the number of categories. And it will be different for the chi-square test of independence. Here you can see the shape of chi-square distributions for different values of the degree of freedom. As the number of categories increases, the peak or the mode of the distribution has a larger chi-square value. You can see here, and you saw that in the previous slide, that the chi-square distribution are positively skewed, and that we find the critical region always in the tail to the right, which is reflected by large chi-square values. So when the null hypothesis is true, the chi-square values are very small and they're not in the critical region. And we can reject the null hypothesis when we find our chi is in the critical region. So it will be a larger value, larger than the critical chi. When you locate your chi-square critical region, we do exactly what we did before. First, you determine your alpha level, so your significant level. So it's going to, for example, be by default always would be 0.05, right? Or is it going to be a 0.01? And then you locate the critical chi-square from this table according to the value of degree of freedom and the significant level. So those are the only two pieces of information that we need. Before we even get to all the calculations, let me show you how you will see this in the literature reported or how you should report it. So the report always needs to describe whether there was a significant difference between the category preferences, and then also it needs to include our chi-square, our degree of freedom, then the sample size, and then if it was significant or not, and to what significant level, so to what alpha level. So summarizing the information for the goodness of fit test, you have one sample and you need to decide whether to use a non-parametric versus a parametric test. Both tests use data from one sample to test a hypothesis about a single population. And it is really the level of measurement that determines the test. If you have numerical scores, so interval or ratio scale variables, you compute the mean and you do a t-test. However, if you decide you have a non-numerical category, so you have an ordinal variable or a nominal scale variable, you compute proportions or percentages and you'll do a chi-square test. So before we get to the actual calculations, let's just look at the observed and expected frequencies one more time, because that's what chi-square is based on. So the frequencies in the sample, the one we have in our samples, are the observed frequencies, so FO. The expected frequencies, FE, are based on the null hypothesis, on the prediction of the same proportions in each category. The expected frequency of any cell is jointly determined by its column proportion and its row proportion. So the FO is just what we have from our sample, so that's just a matter of counting again. But let me show you how we get the expected frequency. Let's use this as our example and apply all of the different concepts. Let's say our research question is, do men and women differ in what they are willing to give up to keep their internet? So we go out, we take a sample of 500 people, and we ask them what they are willing to give up. If they, for example, are willing to give up their morning coffee or their fast food or their cell phone, assuming that they have to give up one of the three things in order to keep their internet because they couldn't afford all of it. So we find in our sample of 500 that we have 87 men who said they are willing to give up their morning coffee. 73 men said they're willing to give up fast food, and 63 of the men said they're willing to give up their cell phone.
113 women said they're willing to give up their morning coffee, 77 said fast food, and 84 said cell phone. So this would be our raw data. And from there, we can easily tally up the total. We find that altogether we had 226 men in our sample of 500. We had 274 women in our sample. That's if we're reading the rows total. If we're reading the columns, we can see that we had 200 people of the 500 that were willing to give up their morning coffee, 150 were willing to give up their fast food, and 150 were willing to give up the cell phone. The row and the column total is important because our expected frequency later is going to be based on these column and row totals. So again, this is our frequency observed. This is what we actually got from our sample. And now we are ready to calculate our frequency expected. What would we find if our null hypothesis was true, that there is no difference? The expected frequency are computed by the same method for each cell in the frequency distribution table. The formula for the expected frequency is frequency column times frequency row over the number of people. So FC is the frequency for the total of the column, and FR is the frequency for the total for the row. So let's apply this. Up here we have our frequency observed, our sample, and then now we want to figure out the table for our frequency expected if the null hypothesis was true. So if there was no difference between what men and women are willing to give up between their morning coffee, fast food, and cell phone. The formula, we said, in order to get each cell for the frequency expected, is the frequency column times frequency row over the number of people. What would the cell for men and morning coffee look like then? All we have to do is take the row total times the column total. So 200 times 226 divided by the total number of people, that's 500. So for the cell morning coffee and men, we get 90.4. Let's do the cell for women and morning coffee. Again, column total of 200 times row total of 274 divided by 500. That's 109.6. You'll notice when you add those two up that it has to be the total that we had in our sample. So you have to come up with the 200 again. So now we can do that for each cell. It's the same procedure for each cell. So you get 150 times 226 over 500. That's your 67.8. Then 150 times 274 over 500. That's 82.2. Again, if you add them up, you'll have the 150. And since you can see in both of them we have the total number of 150, you come up with the same numbers. But let's go through the procedure. So for the cell phone men, take 150 times 226 divided by 500. And then for the women cell phone, 150 times 274 over 500. That's 82.2. And the same thing, when you add up the row totals, you'll see that you have exactly the same values for the totals that you had up here. So you have to come up with the same row totals and column totals. That's kind of your check. The steps for chi-square are exactly the same ones we had before. You start by stating your hypothesis, that is your null hypothesis and your research hypothesis. So if the question is, do men and women differ in what they are willing to give up in order to keep their internet? The null hypothesis is they do not differ. The research hypothesis is, yes, they do differ. Then we set our alpha and we find our critical value reading it from the table. For that we need the degree of freedom. Then we compute the expected frequency, and with that we can solve for our chi-square value. If our chi-square is greater than the critical value, we reject the null hypothesis. If it is smaller, we fail to reject the null hypothesis. For finding our critical value, we know we need the degree of freedom. That's just C minus 1. C stands for categories, and we have 3 categories: morning coffee, fast food, and cell phone. So that's 3 minus 1. We get a degree of freedom of 2. Let's say we have an alpha of 0.05. In the table, we'll see that our critical value is 5.99. So now we finally get to the point where we can compute our chi-square. So here's the formula. Here's our sample data set from where we get the frequency observed. We already made our table for frequency expected if the null hypothesis was true. And now we just have to plug in. It is the sum of the frequency observed minus the frequency expected squared over the frequency expected. So you can see we have to do this for each of the cell combination. 87 minus 90.4 squared over 90.4 plus 113 minus 109.6 squared over 109.6, and so on for each of the cells. So this is what you get for each cell. You should come up with a chi-square of 1.048. So the last step again then is to make a decision. Well, our calculated chi-square is 1.048, but we just said our critical chi-square was 5.99, so clearly ours is much smaller, so it does not fall in the critical region. So here we failed to reject the null hypothesis. In the general population, we can say based on our sample, there is no difference in gender when it comes to what they are willing to give up to keep their internet. Our finding was not significant. Moreover, the chi-square statistic can test for evidence of a relationship between 2 variables. So we know that each individual is jointly classified on each variable, and the counts are presented in the cells of the matrix, or our frequency table that we just saw. The frequency table from our sample is used to test the evidence of a relationship between the 2 variables in the population using this, what we just saw again, 2-dimensional frequency distribution matrix, which is also called a crosstab. And there are 2 different versions. So you can have a single population and say no relationship between the 2 variables in this population exists, or 2 separate populations, no difference between distribution of the variable in the 2 populations. So you can say that the variables are independent if there is no consistent, predictable relationship. Computing the chi-square statistic for test of independence, you can see is exactly the same as the chi-square that we did for the goodness of fit. So the equations are exactly the same. However, different is the degree of freedom, because here you can see we are both considering the row and the column. So the degree of freedom is the rows minus 1 times the columns minus 1. But everything else is exactly the same. And again, let's look at how this is applied. Let's say we want to know if there's a relationship between gender and the fear of walking alone in the dark at night. For that, we would use a chi-square test of independence. So we go out and take a sample of 200 people, and this is what we find. So we find that we had 100 men and we had 100 women in our sample. 23 of the men said, no, I'm not afraid. 77 said yes. 85 of the women said, no, I'm not afraid. 15 said yes. So this is our frequency observed. We know for the formula, in order to get chi-square, that we also need frequency expected. So first we have to create our table for the frequency expected, and we know this is how we do it. The formula, frequency column times frequency row over the number of people. So this is a table we come up with. And again, let's shortly go over it. Frequency column, so for this first cell, in order to get this, we take 100 times 108 divided by 200. That's a 54. Then for the next cell, we take 100 times 92 over 200. That's how we get that. since there's only a 2 by 2, those numbers are going to be exactly the same. And again, if we add it up, we have to still come up with the 100 men and the 100 women, and the 92 that said yes, and the 108 that said no. Now we can just plug it into this formula. So we get frequency observed minus frequency expected for each of the cells. And you can always double check too. You have 4 cells, so you should have 4 calculations here, right? If you have 6 cells, you would have 6 calculations and so on. Now if you do the math, you come up with a chi-square of 77.37. Well, normally you would get your critical value before, but we didn't do that because I wanted to jump right into the calculations. But let's just assume we have an alpha of 0.05. Remember, the degree of freedom is here the one thing you have to watch out for. So the degree of freedom for a test of independence is the column minus 1 times the row minus 1. So in this case, we have 2 columns and we have 2 rows. So it is 2 minus 1 times 2 minus 1. So we get a 1 for the degree of freedom. If you look up the critical value in the table now, you come up with a critical chi-square of 3.84. Well, our chi-square, the one that's based on our sample data, is 77.37. So obviously it's much larger than the critical value. Therefore, we can say there is a relationship between the variable's gender and the fear of walking alone in the dark at night. When we compare the chi-square to other statistical procedures, we can see that hypotheses for a chi-square may be stated in terms of either relationships between variables or the differences between groups. So those are the 2 tests that we did, the independence or goodness of fit. Chi-square tests for independence and Pearson's correlation both evaluate the relationships between 2 variables. Depending on the level of measurement, chi-square, t-test, or ANOVA could be used to evaluate the differences between various groups. So the choice of statistical procedure is determined primarily by the level of measurement. So are we talking about a nominal and ordinal variable, or are we talking about an interval ratio variable? You could choose to test the significance of the relationship by either a chi-square, a t-test, or ANOVA. And we can also choose to evaluate the strength of the relationship, always with an R-square. So once we have a significant chi-square like we just found in our example, it showed us that the difference did not occur by chance. But it does not say anything about the size of the effect. When you have a 2 by 2 matrix like we just had with gender and are you afraid, yes or no, that's a 2 by 2 matrix, right, with 4 cells, the phi coefficient measures the strength of the relationship. Formula for phi is just the square root of chi-square over n. So let's see what this would look like in our example for the problem we just did. And you can see that phi square just provides the proportion of variance that is accounted for just like the R squared. So for effect size, using phi, because we're measuring the effect size for a 2 by 2 table, we use it for our gender and are you afraid of the dark? We had a chi-square of 77.37, so we plugged that into the denominator over the 200 people that we had in our sample, and we get a phi of 0.62197. So now we can say that 38% of the variance in one variable can be explained by the other. And we can say there is a strong relationship between these 2 variables based on our phi. If we have a larger matrix than just a 2 by 2, so for example, if you look at our problem that we had with what are you willing to give up, coffee, fast food, or the cell phone for men and women, right? That's a larger matrix than 2 by 2 because it was 2 by 3. We had 3 columns and 2 rows. So for that one, we couldn't use the phi. We have to use what's called Cramer's V. You can see that the formula is very similar. So we have V equals the square root of chi-square over, and now it's just n times the degree of freedom. And remember, we had 2 degrees of freedom. We had the R minus 1 and the column minus 1. So row minus 1 and column minus 1. So you just got to remember that you always take the smaller one. For 1, we had coffee, fast food, and cell phone. So that's a 3, right? and then men and women is a 2. So it would be the smaller one, 2 minus 1, so we just get a 1 for the degree of freedom. And even so, for that problem, we came up with a chi-square of 1.048. And remember, it was actually not significant since our critical value then was 5.99. But let's say we had a chi-square of 9.48, and we actually did find that it was significant. Because remember, you only do effect size if you found that your finding was significant. If it wasn't significant, you're done. There's no reason to measure effect size if it wasn't significant. But let's assume we had a chi-square of 9.48, and we would want to measure effect size. So we just plug in the chi-square that we would have came up with, and then over the number of people. In that case, we had 500 times 1, because the degree of freedom, the smaller one of the row minus 1 or column minus 1. So we come up with 0.137. And in this case, this would be a weak relationship between the two variables. This table is very helpful for interpreting Cramer's V. So here you can see small effect, medium effect, and large effect for the different degree of freedoms. For the chi-square test, we make certain assumptions and restrictions. So again, we have the independence of observations, meaning that each observed frequency is generated by a different individual. And then the size of the expected frequencies is very important, because a chi-square test should not be performed when the expected frequency of any cell is less than 5. Congratulations, you reached the end of this chapter. Remember, if you have any questions, please email me anytime. Bye. See you next time.